Arjun, actually now let's come to our tape out INSoC 2, right? Firstly, how did it feel holding a chip?
So today by using SOCGen, you can go from 0 to 80% in maybe a week as compared to 3 months.
Wow.
What took,
Right?
what took us 3 months
Yeah.
to go from 0 to 80 for this particular chip.
Hello everyone and welcome back to INCORE's podcast series, The Big Wafer Theory. I'm your host Ajit. This is our second episode and the very first in our Tape Out Diary series. Joining me is someone who needs no introduction at INCORE, our co-founder, chief engineer, and the man behind our Tape Out last year, Arjun Menon. Arjun is a semiconductor security enthusiast who completed his MS at IIT Madras, where he played a key role in the SHAKTI processor program and its subsequent tape out. After his graduation, he started INCORE with his three co-founders to bring out indigenous IP from India for the world, and he currently serves as INCORE's chief engineer and party officer. Arjun, it's great to have you on the podcast. Welcome.
Thank you, Ajit. Nice to be here.
Great. Arjun, let's get right into it. You've been working in semiconductors for a while now. Could you give us a brief about your journey? What first got you interested in the space and what has kept you hooked in the space?
Right. So I've always loved VLSI, both analog and digital, back from my BTech days. But if I really had to trace it back, it would be to my mother, who was also a VLSI design engineer at Semiconductor Complex back in 1990s. So yeah, I remember visiting a fab when I was about 5 years old, and I guess that's where the interest started.
Wow, 5 years old. Semiconductor complex, you mean SCL?
Yes.
Oh, in Mohali. Wow.
Yeah.
Okay, that's crazy. Amazing. So, what led you to starting INCORE? Like, I know INCORE's founding team has diverse backgrounds, right? How did you all come together and what was the vision behind INCORE?
So all of us met at IIT Madras.
Okay.
I was doing my master's. Neil, our CTO, was doing his PhD, and Madhu, the program manager of the so-called SHAKTI program. The three of us were part of the journey ever since 2013.
Oh.
We met Gautam on our way when we wanted to tape out SHAKTI. Gautam came in from Intel and helped facilitate a free tape out
Okay.
of SHAKTI on the 22 nanometer fab. That's where the four of us met. But the whole SHAKTI program actually started off as an academic effort. When we wanted to work on processor design and we wanted to do research on processors, what we felt is that there was not a good standard open source processor that was available on which people can develop and even people can use for teaching microprocessors. That's how the SHAKTI effort started. But when we designed the first SHAKTI processor, the SHAKTI C class, and we started talking to people, especially people like IG Card and ISRO, we understood that there is a huge need for such processors even within India. And hence, we thought it made sense to start INCORE and commercialize what we built.
Indigenous processors, so to say, would be the gap that you were trying to solve. Is that right?
Yes, for sure. I think India as a country does need to own its own chips.
Yeah.
Today, we are importing almost everything, which is not good in a long scale. And
Security perspective. Yeah.
yeah, for sure. I think in the strategic sector, security is indeed a big concern. Today, we are importing processors which we do not know what is there inside each of these processors. So especially for strategic sectors, it is important to own the entire solution and right down to the last transistor that you're manufacturing. So yes, it made sense to design processors and subsystems and IPs in India that will be used, of course, within India and also in the world.
Got it. And that's when 5 years post SHAKTI, you guys started it in 2018, right? And then, yeah, understood. To your role at INCORE as chief engineer, what does your day-to-day look like? Like, what does the chief engineer do?
I basically help unblock people across various design departments, and I personally contribute to projects wherever there is a pressing need,
Okay.
or where we are time crunched, or where there is a resource constraint. I primarily also take care of all security IP at INCORE, but I work on all IPs including cores, fabrics, peripherals, uh, at times as an FAE, at times a bit on software, and of course the tape out that we did
Got
at INCORE.
Moving to the chip design journey for INSoC 2, right, that we undertook last year. Just before we dive into our own chip, can you give a brief walkthrough of the chip design journey from concept to tape out? How does it look like? Feel free to go as technical as you'd like here.
Of course. So any chip design, first of all, starts with a specification. You're trying to solve a problem, and you would first come up with a specification of the SoC that you want to build. So this would include what core, how many cores, what peripherals do you want to put in, what is your main communication bus, do you have multiple levels of fabrics, how many IOs, and so on. Once you have a notion of what the SoC is that you want to build, you would then go ahead and write the RTL for that particular SoC.
Okay.
Typically, people use languages like Verilog or VHDL, but at ENCORE, we use a high-level synthesis language called BlueSpec.
Okay.
Just how assembly is to C program is how Verilog is to BlueSpec.
Okay.
Right?
So a higher abstraction.
Yes,
level, right?
BlueSpec gives you a much more higher abstraction, and that actually lets you write code which are much more modular and much more parameterized.
Got it.
Also, BlueSpec gives you 100% synthesizable code output.
What does that mean? What does 100%
Right.
synthesis?
So in Verilog, if you write a code, let's say you have defined a variable called reg, it does not necessarily mean a register. It depends on how you use that particular variable, and that will define what the inference of that particular variable is. But in BlueSpec, if you have defined a reg variable, it definitely translates to a register. In Verilog, it can turn out to be a register, it can turn out to be a latch, right? And that causes problems. So if you're designing something in Verilog, you are not sure if you can actually tape out that particular RTL. You'll have to go through certain steps to check if this code is indeed realizable in hardware.
Okay.
That's called being synthesizable, right? But BlueSpec code, when compiled, gives you synthesizable code for sure.
Got it.
So after you've written your SoC in an RTL or BlueSpec,
now you have that 100% synthesizable code out of BSV.
So BlueSpec, again, if you compile BlueSpec, you would get a Verilog code out of it, which you can take through rest of the flow. After you've finished your design, the next step is, of course, verification. You would have to thoroughly verify if what you've designed works correctly.
Yeah.
After verification, you would then do linting. Linting is the process where you check if your design has any other flaws. For example, are there latches being inferred in your code? If you have multiple clocks, have you ensured that the data movement between clocks is synchronized? And so on. So there are a whole bunch of checks that need to be done, and those are done during linting. So after you're done linting, the next step is to do synthesis. Synthesis is basically the process of mapping your design with the standard cell libraries that are provided by the foundry. So if you have an AND gate, an OR gate, a MUX, and so on in your design, the process of synthesis will take all of these cells from the standard cell library and give you a netlist with all of these standard cells placed. Now, the input to synthesis are three things. One is, of course, your RTL source. The second is the constraints file. In this constraints file, you specify various things like what is the max frequency that you want to attain, what is the max power budget that you have, and what is the area that you want this to fit in. In this constraint, you'll also specify what are your various input-output delays and a whole bunch of other stuff. The third thing is the synthesis script itself, where you specify what options of the tool would you like to exercise. Do you want very high optimization levels, or do you want a low power design? Do you want to enable clock gating? Do you want to preserve hierarchies of modules?
Okay.
So with these three inputs, the synthesis tool basically gives you a netlist as output, which you again take through the backend flow.
Okay.
After synthesis, the next step is basically to ensure that the output of synthesis and the input RTL to synthesis were indeed the same. This is called LEC, or logical equivalence check, where you feed in the input RTL and the output RTL, and you check, and the tool checks if both of them are exactly the same. This ensures that your constraints were correct and the tool has indeed produced the right output.
Okay.
After LEC, the next step is the entire backend flow.
Okay.
The very first step in backend is floor planning.
Okay.
And partitioning. So first of all, if your design is very big, you would partition it into multiple smaller designs. But let's probably pick the simple case of a single unified design where you don't have partitions and you just have a single top level module. In this top level module, you would still go ahead and try to place big items. For example, if you have an SRAM block, you would try to place that manually.
Okay.
If you have IO pads, you would try to place them manually. Likewise, if you have IPs like PLL and so on, you would also decide where to place the PLL appropriately. Okay. The next step is basically coming up with the power rails. So all standard cells, all IPs would require power. You would basically draw out how your power grid should look like. Of course, all of this is an iterative process. You cannot get it right in the first go. You would first come up with some power architecture of how your VDD and VSS lines should go, and then eventually you come back. If you see that there are problems in this, you would come back and again replace them. Once the power planning has been done, the next step is basically placement. In placement, the tool tries to place every single standard cell that has been instantiated in your design.
Oh, wow.
And it tries to ensure that it does so within the constraints that you've provided. After placement, the next step is clock tree synthesis. Almost all registers and a lot of macro blocks would need a clock to work with. It's important to enforce that the clock that comes to each of them have very little skew.
Okay.
So the next step is clock tree synthesis, where you try to route the clock to each of the registers and other hard IP blocks which require clocks. The tool basically ensures that the clock tree that gets synthesized is indeed balanced, and it places buffers at the appropriate places to ensure that. Once the clock tree synthesis is done, the next step is routing. Routing is where you connect all of these various standard cells that you've placed.
Okay.
Again, in routing happens in multiple layers. Just like a PCB, a chip would also have multiple different layers in which you can route. Typically, when you're doing a test tape out, the number of layers does not matter. You are free to use as many layers as that particular process gives you.
Okay.
But if you're doing a commercial tape out, where if you're trying to design a chip that is going to be manufactured at scale, it matters the number of layers that are there in the chip. And it is also important to optimize on the number of layers, because if you have more layers, the cost of the chip again goes high, right? After routing, the next step is to ensure that the output of this routed netlist is same as the input that was fed in. So you would again do an LEC between the synthesized netlist, which was the input to the place and route tool, and the output of the place and route tool.
Okay.
Once this has been verified, the next step is to ensure that there are no design rule violations. Of course, while you do routing, there might be some shorts that would have occurred. There would have been some wires whose widths would have been much lower than the minimum specified width. or two standard cells that have been placed way too close. So you then run DRC checks to ensure that none of these violations are there. If you're not able to resolve all DRC violations, you may have to go back and change your initial floor planning.
Okay.
You may have to give some space between different IPs. You may have to specify certain regions, saying that, hey, you know what, in the initial stages, do not put any standard cells in this. So these are called placement blockages. Likewise, you may also want to say that there is a particular space where there is too much of routing happening, and you see that that is also a problem.
Okay.
Right? So that's where you kind of spread things out, and you may also place routing blockages in some places so that wires don't go through certain parts, which you can again use at a later point if you want to resolve these shorts. So you iterate this, and then finally, after a couple of iterations, you would get a DRC clean netlist. At this point, it is also important to make sure that once you have a DRC clean netlist, you would then run a very detailed timing analysis. So you would do timing analysis across different temperatures. You would also have process variations. So even though all of these chips are going to be designed very identical, I mean, it's the same design that you would be replicating, what happens is that when you actually manufacture them, there will be variations amongst each of these chips. So some of these chips may run faster and some of them may run slower. And these are called process variations, and it is important for you to ensure that even in the worst case scenario, which is called the worst corner, your chip should still meet all the criteria that you have put forward.
Okay.
Hence, you do static timing analysis across all process corners and various temperatures to ensure that your chip indeed will work in no matter what the condition was. After this process, you would generate what is called the GDS2. This is the file that would be sent out to the fab for tape-in, which the fab again takes in and then goes ahead with the manufacturing process.
Got it. Okay. That was a very good deep dive. Thank you so much, Arjun, for that. Actually, I just had a very small query there. Like, what in this process, very briefly, would change if, let's say, we choose a TSMC 22 versus a TSMC 45? Like, between different processes, how would this process look like? Would it remain the same, or is it just the libraries that we choose that will change?
Right. So, again, we work primarily on the digital front end.
Correct.
For analog, a lot of things would change.
Okay.
But again, I think the process is more or less very similar until down to probably 7 nanometer. But beyond that is a lot more different. So for the scale that we are operating at for embedded systems, it doesn't really matter much whether you're using 45 or 22. The process would more or less be pretty same.
Got it. Okay. Arjun, now let's come to our tape out, INSoC 2, right? Firstly, how did it feel holding a chip that's been months in the making? And I see that you've gotten our chip. Can you just show it to the audience and tell us how you feel?
So it was a great feeling the first time we got this chip back. It was really nice to see it booting. I think all of our engineers, they've been working long, and it's been in the works for almost 7 months. And of course, the IP development started even before that, right? So when you sit and write code for a couple of years without actually having a physical thing to touch it, and after these many years, when you tape it out and you get the physical chip back, you put it in a board and you see it booting, that's an out of the world experience. I think the whole team, everybody was really happy just to see it boot.
Yeah. Okay. Amazing. Could you actually describe the process we went through for this tape out, the timelines, and why we decided to tape out last year as well?
Of course. So technically, it is pretty similar to the process that I described a while ago. But when we started selling IP, we were constantly getting asked, is your IP silicon proven? Have you guys taped out? Can I get a chip which I can run some tests on and run my software on? And the answer was always no, but something. right? It always started with a no. But of course, we did have FPGA ports on which people could run software, but that did not cut the mark. So it was really important to silicon prove your IP, which is true in any semiconductor business, that unless you're silicon proven, it is very difficult to sell that particular IP.
Yeah, even for a fabless company, and we are self-proclaimed fabless, right? Like, shouldn't our IP just? Why is this need to silicon prove our IP?
Right. So in a typical scenario, if you are designing something, you can cut corners. You can, of course, show some parts of it working on FPGA. There can be ifs and buts, but once you tape out a chip, you are 100% there. You have verified the IP. You have done all the required checks that need to be done, and you have taped it out and silicon proven the design. Anybody can now take this chip, run software on it at a much higher frequencies than what is capable either in simulation or on an FPGA.
Okay.
Right.
Could you share any milestones that we achieved through this tape out?
Yeah, for sure.
Yeah, I know we used one of our proprietary platforms to make the chip. Yeah, maybe you can share more.
So while we were designing this chip, initially we thought we will just tape out a single core system. Then we decided maybe 2 cores. And then it went to 4 cores, and then it went to 6 cores.
Wow, okay.
And even the number of peripherals. Initially we thought we would put probably 10 peripherals, and that number kept increasing. We said let's also tape out all the security accelerators that we have. So when the chip architecture itself kept evolving over time, what we realized is that when we tried to manually stitch everything up, it was taking too much time and verification effort to ensure that everything is being done correctly. And hence we started automating this connection, right? And towards the end, we had a tool which could automatically stitch up different classes of or families of cores together and different instances of them with various different configurations. All of this was automated. And I think that was a very good learning experience from us. And the whole SOCGen tool came out of this experience what started off as an internal tool to solve the internal problems eventually turned out to be a tool that was useful for our customers also.
Yeah, that's what we are about.
So that was a really good learning experience and a really good thing additional thing that came out of this tape out experience.
Got it. And that was a huge milestone for us, right? Proving SOC generator along with those 6 cores that you're talking about.
Yes.
Are all of these 6 cores the same series of our cores or?
No. So the 6 cores, 2 of them are calcite series of processors and 4 of them are azurite series of processors. But even within them, the ISA configuration of each of them is different. So there is a core that is RV32I. There is some other core with a multiplier. There's something else with a floating point, and a 4th core with a floating point and a bit manip extension. So all the cores are different in their structure, and of course across 2 families of cores.
Nice. So how did this experience of taping out with INCORE compare with any of your previous tape outs? And I know you were working with SHAKTI and you were part of the first tape out that happened with SHAKTI, right? Yes. How would you compare tape outs from an academic to a commercial setting?
So back in SHAKTI, I still vividly remember the SHAKTI tape out days because that was the very first time we were doing something. And moreover, when you're in an academic setting, you probably don't have people who have done this before. Of course, you can talk to people who have done this before, but there would not be somebody working full-time there who would help you design the chip. So me personally, I spent about 1.5 months at SCL Chandigarh, where I learned how to do backend, and I did the backend with their help for the entire chip. And that was a huge learning experience for me. And frankly, when I was doing the backend, I was not entirely sure if this chip would work, right? And even when we signed off everything, we gave them the GDS2 and I came back, I was really doubtful if the whole chip would work or not, because that was the first time I'm doing it. And we were really happy that when we got it back and the chip actually booted, I think everybody in the team were really happy that the first chip that was both designed and manufactured in India indeed did work right at the first go. So I think the first time you do it is very different from the subsequent times, because the second time you know what to do, right? And you would know what the common pitfalls are. That said, there is still a very big difference in an academic tape out versus a commercial tape out. In an academic tape out, it's fine if you have not spent way too much time verifying the IP, because you're trying to prove certain things in that particular academic tape out. And people don't expect it to be completely verified, foolproof for every single scenario. Whereas if I'm taping out from an industry, be it a test tape out or a production grade tape out, verification is mandatory, and verification to meet industry standards. Verification that meets industry standards is mandatory. So this particular chip has gone through immense amounts of verification. But again, because this was a test tape out, we did not spend way too much time optimizing on the back-end flow. For example, using lesser number of metal layers or anything. We did not spend any time on that, because this is a test tape out and not a production grade tape out.
Got it. So on verification, if I had to double down, when do you know that it is foolproof? When do you know that it is 99% verified? Like, when do you stop?
Right. So verification is probably a whole different podcast, but overall, I would say that there are standard metrics, right? So you have code coverage, which is like the very first basic level of verification maturity, right?
Okay.
So you would try to hit 100% code coverage, right? The next is, of course, you write functional cover points. You write enough of them that basically capture some functional scenario, and you ensure that your test cases are able to hit those particular functional scenario. Again, verification itself is an art. There is not one right way of doing verification.
Okay.
You would have to do 100 different things, and if everything works, then you are confident enough that it works, right? And at INCORE, we have a huge team working on verification, where we use embedded UVM and a whole bunch of other tools to ensure that all the chips that come out are verified.
Verified and validated. Nice. Okay. What were some of the toughest ordeals or challenges during this INSoC 2 process that we at INCORE had faced?
So I think on the technical front, again, because this was a purely digital chip and it was not a production grade tape out where we had to optimize the last millimeter square out of it, there were not way too many technical challenges, but what we did face was issues with respect to things after manufacturing, for example, packaging and so on. So initially we had fixed a particular package, but then later we realized that that package is not really compatible. There is no socket available for that package. The lead times were high and so on. So I think we went a bit back and forth on the packaging front, which caused some delay in the overall timelines of the chip getting to the board. But other than that, I think it was pretty much...
So packaging was one of the major challenges.
Yeah.
What about foundry logistics? Any challenges there from within India?
So foundry logistics, of course, we taped it out at TSMC. You cannot directly talk to TSMC. We went through IMEC, and IMEC indeed interfaced with TSMC. I think the TSMC timelines were pretty perfect. They were to date. We submitted the GDS, and within the right timeline, we did get a GDS back.
Got it.
What took time was packaging after that, where you had to ship the unpackaged die from one country to another, and then get it packaged somewhere else, and then bring it back to India, where you would have import problems. Customs and so on.
All of that, yeah.
So that logistics is where we took some time. But I think with the setting up of a lot of these fabs and packaging facility in India, we would be able to considerably reduce the time and effort taken to package these chips. So I know that one of the latest SHAKTI chips were packaged by the Tata Foundry, and that was a pretty smooth process, and they had a pretty good experience with that packaging. So hopefully with our next tape out, we will try to package it within India.
Within India, right? Amazing. So while during this tape out process, I know that we did the entire front end ourselves, right, in house, but we did not have a back end team of physical design engineers. What did we do for PD? And if we had outsourced it, and I know we outsourced it, how did we ensure that the deliverables that came out were, good enough, because it will make or break the chip, right?
So INCORE today does not sell chips. We design IP and tools. We sell the IP to our customers, and the customers go ahead and tape out the chip. That basically means that we will probably do 1 or at max 2 tape outs a year, typically for the next couple of years. And for these numbers, it does not really make sense to own the entire PD flow and have PD engineers in-house for us to do it, especially because we are also not trying to optimize every last square out of the flow. And moreover, we are a purely digital design company. We don't design any analog components. So there's that. That said, I think it makes sense for us to outsource PD. So we work with a company called Chakra, which is again a startup from IITM, where we outsource the entire backend process to them. Now, of course, when you're outsourcing something, you have to know what the process is, and you will have to have a reasonable understanding of the flow itself. But today's tools are so good that it will tell you if there are any problems. In fact, the last step that I mentioned the DRC rule check step, where you ensure that the design does not have any issues. If there are any issues, one, the tool would pop it up, and second, if you send a GDS with these issues to the fab itself will not accept it.
Oh, okay.
Right? So the fab will come back and say that there are some issues that you would need to resolve. So one, you look at this report, of course, there might be some issues or some design rule violations which you may be able to waiver. But as long as you have good understanding of what these violations means and are they okay or not, that is good enough. Also, we have LEC in place. So the RTL that I give them will be verified against the final design that they give me back. I can do an LEC and ensure that the design I gave them is same as the design that they gave me back after place and route.
Okay, understood. Okay. In terms of foundry logistics, how important is it that India gets its own fabs in the next few years?
I think it's really important for India to get its own fab, and which is already in place, which is already in progress. India is a huge consumer of electronics, right? It doesn't really make sense for us to import all the electronics that we are consuming. It would make total sense for us to manufacture it here and sell it locally. Again, the foundry business is more of a logistics business rather than high technology. Of course, there is high technology, but all of that is being imported. There are people who have the technology who would come and give us that technology and set it up. But in order for a fab to be profitable, it's really important that everything runs smoothly and efficiently and with low cost. India has a very low cost structure throughout all aspects, and I think that would really mean that the fabs of India will make a lot of profit.
Yeah.
Second, for strategic sectors and for critical infrastructure, it is important for us to own the design and own the manufacturing process.
Yeah.
so that no third party can introduce Trojans in this process. So if you're designing a chip to control our nuclear reactors or something that we are putting in satellites or missiles, it is important that we own the system end to end. Today, though we can do the design, and we have done multiple such designs. As part of SHAKTI, we designed one chip for ISRO's launch vehicle, which was also manufactured at SEL Chandigarh. SEL has 180 nanometer, which is a reasonably older technology, but with the new fabs coming up, I'm sure that we can design almost all critical chips. Right in India.
Yeah, indigenously. That's the way to go. Coming to post tape out, what's the post tape out process been like for INSoC 2 since it came back from the fab at the start of the year?
Once we got the chip back, we designed a board for the chip, and we ran some basic tests to ensure that various parts of the chip work correctly.
Okay.
Of course, the board bring up process was pretty exciting, but it didn't take us way too long. It took us about 3 days for us to mount the chip and get it up and working. Post that, we have been trying to develop some software so that we can showcase the various applications that can run on this chip.
Nice. What applications are you planning to run on the chip?
Yeah, so the chip today is capable of running any RTOS. So we will be running Zephyr RTOS, which is commonly used by a lot of people. And we will run, say, an IoT application where this device will act as an IoT endpoint and will share data to an IoT server. And then you will be able to read the sensor data out or communicate from the device to the server.
Nice. Okay. This particular board and chip that we have, can anyone license it from us today, or is this just to prove internal capabilities?
So this particular chip is a test chip, which was again designed and manufactured to silicon prove our IPs, and hence we are not selling this chip.
Okay.
That said, if some of our partners and customers want to test out some of the software, we would definitely lend them the chip. So that
if let's say someone wants to test RTOS on Azurite specifically, you can probably show them that this chip will run.
Yes. So if our customers want to test if an instance of Azurite and an instance of calcite works, and if they want to run some software and test it on the chip, we would definitely lend the chip to them.
Okay, amazing. Awesome, Arjun. Thanks so much for talking so much about INSoC 2 and giving us a good overview of what the tape out process looks like. Now a little bit on the extraneous things around the tape out and the chip industry itself. First up, AI. Did you or the team employ AI at any point in the chip design?
So we did employ a very little bit of AI while we were designing the chip, right? And even when we were automating, when we had to write Python code for various automations and scripts, we did use AI a lot. But post that, I think the use of AI has increased a lot within INCORE. Today, we use AI for writing new code, we use AI for debugging, we use AI for verification, and for other automation tools.
How would you say that has impacted timelines of chip design? Let's say, like, this chip took us 7 months. With AI coming in, what would you presume it would have taken? Like, if we were to do whatever we're doing right now from last year.
Okay. So in VLSI, everything needs to be deterministic, right? You cannot just put an AI tool blindly and just consume the output. That said, what would reduce time taken to design this chip today would be just using our tool, SOC
generator,
right?
Good marketing,
Right. So today, by using SOCGen, you can go from 0 to 80% in maybe a week, as compared to 3 months.
Wow.
What took us 3 months to go from 0 to 80 for this particular chip.
Okay. Got it. All right. That's it on the tape out side of things. What advice would you give to any engineers or early stage startups that are potentially trying to tape out right now?
Well, my first advice would be to people who are thinking about startups. I would say
In this space, yeah.
in this space, I would say that this is the best time to start a company. The government is pushing really hard for Make in India and even design in India. So this is the time to build in India if you're interested in building a company in the semiconductor space. That said, if you're a new person who has started a company and who's planning to do a tape out, ensure that you have somebody or you are able to talk to somebody, you have a consultant who has done this before and would be able to help you out across various stages of the tape out. It is also important for you to fix the package much earlier in the design cycle because that will dictate certain criteria in your physical design as well. So fix the packaging, ensure that this packaging has low lead times, you have the cost of the packaging is low, and if you're doing a test chip, maybe do you have standard sockets that can fit in these packages and so on. Logistics is something that we techies do not pay a lot of attention to in terms of planning, but I think that is something that all of us should definitely look at of what are these timelines and where can you get all of these possible delays and ensure that you mitigate those delays.
Yeah. Okay. Got it. I see you mentioned hire a good consultant to go through this process. Does INCORE engage in consulting of sorts for tape outers?
So we would definitely help people and we can let you know the things that we went through and some common pitfalls that happened during our tape out experience. Why, if you're a startup that has not done this before.
Got it. Understood. All right. What's next for INCORE and its chips? When are we planning our next tape out?
Right. So our next tape out would be a dual issue multi-core processor.
Wow, that's a huge leap from...
Yes. With a memory controller and of course all security IPs. Right. This would be a high performance embedded core running at more than a gigahertz clock frequency. And that is scheduled sometime mid next year.
Oh, great. Yeah, looking forward to that chip and the podcast that comes after that.
Of course.
Yes, that's it on all the things engineering, Arjun. As a sign-off note, what's a book, technical or non-technical, that you would recommend to our audience?
Yeah. If you're somebody who's against planning to start a company or you're an entrepreneur already, I would highly suggest reading this book called The Hard Thing About Hard Things by Ben Horowitz.
Okay.
Here he talks about, I think this is one book which presents a very grounded and real struggles of building a startup. And I think any startup founder, once they read that, it would change the perspective of them about what it means to build a startup.
Yeah. Amazing. Thank you so much for the recommendation, Arjun. Also, Arjun, thank you so much for walking us through the journey from spec to silicon. It's rare to get such a clear look at the challenges, choices, and precision that go into, taping out in general. Right? For our audience, I hope this episode helped demystify why tape outs matter, why they're very tough, and why they're such a big milestone for a fabulous company like INCORE. We have a lot more podcast episodes coming up from behind the lab doors at INCORE that will cover tape outs with other clients that we are taping out with as well. So thank you for tuning in to this particular episode and stay tuned for the next one. See you.